Hello everyone, and welcome to Introductory Astronomy. I am your instructor, Dr. Raja Al-Mukahal. In this video, I want to welcome you to class, and I want to review the basic mathematical techniques that you will be needing for this course. As you may know, this is a course designed for non-science majors where the mathematics is kept at a minimum. You will not be doing any algebraic manipulation or using the quadratic formula or finding the roots using synthetic division and so on. You're not going to be doing any of that. However, you are expected to do some basic mathematical calculations, such as entering data into a formula and coming up with an answer. Being able to understand basic geometric shapes such as the ellipse and the circle and the parabola. Being able to convert a large number into scientific notation, or taking a scientific a number written in scientific notation and multiplied by another number that is written in scientific notation, and so on. So those are the basic techniques that you need to, you are expected to know as a college student, regardless of your major. So I want to review all these mathematical techniques together, and hopefully this will going to be very helpful for you and help you succeed in this course. So the first topic, there are several topics I want to go over. I'm going to try to make this video less than an hour, I hope. The first topic that I want to cover is scientific notation. So let's begin. So when we say scientific notation, and I'm sure you probably have studied it already in high school, scientific notation, the reason scientists use scientific notation is because when you deal with a very large number, scientific notation allows you to write it in a compact form. For example, let's say I'm dealing with the mass of the Earth. Well, the mass of the Earth is a number that is 24 digits. Imagine that, 24-digit number. Well, how am I going to write it down and say I'm going to multiply by another number that is 24 digits or 26 digits, dividing it by some number that is also 27 digits, and so on. So it would be extremely cumbersome, extremely difficult, extremely tedious to deal with such large numbers. So scientific notation is a way to write that number in a brief form. You see what I'm saying? Another reason for the scientific notation is if you are dealing with something that is extremely tiny. For example, let's say the mass of the electron. Let me write it down for you. So the mass of the electron, it's scientifically it's written as 9.11 times 10 to the negative 31 kilogram. What that means, if I'm going to write it in natural number, it would be something like this: 0.00031 zeros until I go with 911 down there. So there will be a very large number of zeros. Again, this is very unrealistic. Back to the mass of the Earth. I believe mass of the Earth is roughly 6 times 10 to the 24, approximately, which means that's 6 and 24 zeros. As you can see, it is totally inconvenient, totally impractical to keep writing such really small numbers like this one, or very, very large number like these. So scientific notation comes to the rescue. Okay, so how do we do it? Let me just give you basic examples. Let's say, for example, I have the following number: 63000. Okay, and I want to write it in scientific notation. The first thing you need to do is to locate the decimal point. Okay. As you know, the decimal looks something like this. Let's say I have the number 4.2. So this is the decimal point right here, right? So usually, if you see a number like this, as you can see, the decimal point is not shown. It's invisible. But by default, if you don't see it, by default, it will be to the far right of the number, which is basically right here. You see what I'm saying? So what I want to do, to write it in scientific notation, Okay, well, I forgot to mention something. Scientific notation looks something like this. You have a number, decimal point, and then probably two numbers, mostly, multiplied by 10 to the power of plus or minus a number, or maybe a two-digit number. This is how scientific notation look like. Mostly, not always, but most of the time it has this. It takes up this form. Look, for example, look at the. Let me bring it down. Look at compare this with the mass of the electron. See, 9.11, which is right here. So that can put 9.11 times 10 to the power of minus, so we chose the 31 is right here. You see that? So that's how it's written. Or, for example, look at the mass of the Earth. It is 6.0, we can say, or 0.00 times 10 to the 24. The 24 here is positive. We don't need to put the plus. But as you can see, this is how it looks like. So they, in your mind's eye, the scientific notation looks something like number, decimal, number, digit, times 10 to the power of plus or minus some number or double-digit number there. Okay? Something like that. So with this in mind, so I want to write now this number right here in scientific notation. How do I do that? Here's how you do it. You take this decimal point and you move it all the way here between 6 and 3, because I want to put it in this form. Digit, see that digit? Yeah, let me use a different color. I'll use red. Okay, so as you can see here, digit, and then a decimal, and then digit. So that's going to be, so what I want to do, I want to move to this, to the decimal between 6 and 3. So I have to take steps. So how many steps? 1, 2, 3, 4. So what that means, this equal to 6.3000 times 10 to the, because I moved to the left, it's positive 4. I don't need to put the plus. So now I can write it, the zeros here don't mean much, so basically it becomes 6.3 times 10 to the 4. There we go. Got it? Let's say I have the following number. Let me go back to black color. So let's say I have the following number, 0.00656, okay? And I want to write it in scientific notation. So the question is, where should I put, okay, I can see the decimal point right here. Where should I put the decimal point when I write it in scientific notation? It should be right there, right? If you follow this rule here, it should be right here. So how many steps is that? 1, 2, 3. So I get 3 steps, and I'm moving to the right. That's a minus. So it becomes 6.56 times 10 to the power of how many steps? 1, 2, 3 to the negative 3. And there we go. This is how you would write it down. Okay? Good. I mean, if you need more examples, again, I'm trying to make the whole explanation in brief. I don't want to talk too much, but if you need more examples, you may want to consult maybe YouTube. Just type in something like scientific notation. I'm sure lots of videos will come out, and then you can watch more videos on how to do it. But that's basically what it is. It's not going to get, you're not going to see something harder than that. Okay? Now, let's say I have two numbers and I want to multiply them together, and they're both written in scientific notation. Okay? In this case, I mean, in modern day, you just use a calculator, and the calculator will take care of that for you automatically, and that's perfectly fine. Okay? So let's say, for example, I have the following two numbers. 8.43 times 10 to the power of 8 multiplied by, let's say, 2.21 times 10 to the power of negative 5. All right? So if you want to do it without using, if you don't have a scientific calculator, so what you do, you basically, let me change the number, the color. So what you do, you multiply 8.43 times 2.21 and then times, and then you multiply the power of 10 here together. As you know, 10 to the 8 times 10 to the negative 5, that'd be 10 to the 8 minus 5, so that will be 10 to the third. You see what I'm saying? So that will be 10 to the third here. So all I need to do now is just use a calculator to calculate that. And when I do that, I have my calculator with me, I will get 18.6 times 10 to the third. I can finish here and that will be good enough. But however, look at in scientific notation, as you may recall, it's only one digit to the left of the decimal point, and then the rest is after the decimal point. As you can see here, I'm trying to get that, there we go. As you can see, the decimal point here, I have 2 digits to the left. So what I want to do, I want to move it just once here, and notice that I'm moving to the left. That makes it positive, so that will be 1.86 times 10 to the 4, right? Because I moved it one step, so that's a one step. So you just add it to the number here, and it becomes a 4, and there we go. That's how we calculate that. Okay? All right. One more example. Let's say we want to divide the numbers. So let's say I have 5.6 times 10 to the negative 3 divided by 2.8 times 10 to the negative 6. Okay. So again, I can, if I don't have a scientific calculator, which I encourage you to get one, get just the basic calculator. And that will take care of all of that automatically for you without doing any of these calculations that I'm showing you. But basically what you will do, you want to divide these separately from these, okay? So basically you're going to have 5.6 over 2.8 times 10 to the negative 3 divided by 10 to the negative 6. I'll come back to the second ratio in a second. So when I use my calculator for 5.6 divided by 2.8, that's almost exactly 2.0. Okay? That's basically 2.0. Okay? And then how do I deal with the next one? Well, as you may know, x to the m divided by x to the n, that's equal to x to the m minus n. Remember, when you move it up here, you change the power, the sign of the power. So I'm going to do the same thing. So that becomes 10 to the negative 3 plus 6. You see what I'm saying? And that will be equal to the final answer, 2.0 times 10 to the power of 3. And there we go. It's written properly in scientific notation. Okay? Okay. Looking at my notes here before I move on. Oh, one more thing. Now, what about if I have a formula? Okay, this is where it becomes important to learn about the scientific notation. What if I have a formula and I'm gonna enter a number in the formula that is written in scientific notation. Let's take the famous formula, Einstein's formula, E equal mc squared, for example, okay? Where you may know that c here is the speed of light, and it's equal to 3 times 10 to the 8 meters per second, okay? So basically, this is the speed of light in meters per second. I'm going to enter it into the formula in c squared here. And let's say the mass, let's pick any mass. Let's say the mass is 0.1 kilogram, for example. Okay, so 0.1 kilogram for the mass, and the speed of light is 3 times 10 to the 8. So let's plug him in there, and I will show you how to do that. So in this case, the energy, the mass is 0.1, it's right here, times c squared, so that's 3 times 10 to the 8 quantity squared, instead of saying. Now again, using the calculator will give you immediately the number, but if we want to do the algebraic manipulation here, as you may know, if I have x to the n times, let's say, x to the m, all of that to the power of, let's say, p, that basically what you do, you take this p and multiply by n, you multiply by m. It will look something like this: n x to the power of np times x to the power of mp. You see what I'm saying? You basically, if it's squared, you're going to square everything in there. That's all. That's all I'm saying, okay? So anyway, so we have 0.1 times 3 squared times 10 to the 8 times 2 is 16, okay? So that will be 0.1 times 9 times 10 to the 16, okay? So we have here 0.1 times times 9 is 0.9 times 10 to the 16, and that'll be basically the final answer. But if I want to put it in the proper form, remember the proper form is number, decimal, number, times 10 to the power of plus or minus some number here, right? So that would, so what I mean, what that means is that I want to put a number to the left of the decimal. So basically I want to move the decimal just one step right there. So it becomes something like 9.0 times 10 to the, now since I moved it to the right, that's a negative 1. So I can say times 10 to the negative 1 times 10 to the 16. So that will be 9.0 times 10 to the 15. You see what I'm saying? And that'll be the final answer for this formula. Okay? Okay, good. So that's basically how you use scientific notation. I don't think you're going to get anything harder than what you have just seen, okay? Now let's move on. Let's move on to the next topic, and that is, entering numbers into a formula, but those numbers are not necessarily written in scientific notation. For example, later on in the course, you're going to deal with something called Kepler's laws, and that is something called Kepler's third law. Kepler's third law. We'll come. I don't want to explain it now. I just want to deal with the formula itself. We will learn all about it later. But it's called Kepler's third law. It's a mathematical law, and it basically says p squared equals a cubed, okay? Where p here is the period. Period means the time it takes to complete one cycle. For example, Earth, it takes Earth 365 days to go around the sun, so we call that the period of the Earth. The period of the Earth is 365. Or the period of the moon around the Earth is, 29 days, and so on. So the time it takes an object to go around in one orbit, they call it the cycle, it's called the period. And A here is the radius of that, let's say, for example, here is the Earth going around the sun, and here is the sun here, and this is the radius, we call it A. In some books they call it R, but in astronomy books I think a more common notation for it is A rather than R, okay? So, and of course that's basically the radius, okay? So Kepler's third law, written in this form, so the period squared is equal to the radius cubed. Now the question is, for example, here's an example. Let's say, for example, that the period given to us to be equal to 4.2 years, okay? So we have an object. It takes it 4.2 years to go around its own star, parent star, for example, okay? And the question is, what is the radius of that orbit? You know what I mean? So basically he's looking for what is A here. Given P, sorry, let me go back and put it right. So basically, given P, right there, what is A? Okay, and notice that we have powers here. So how do we do this problem? So all you do is simply plug it in immediately. So we have basically, I'm solving for A, so it's going to be A cubed equal P squared. I haven't done anything yet. I'm going to put the P squared, the P is of course is equal to 4.2. It's going to be 4.2 quantity squared That's a cubed. Okay. Now, the easiest thing to do, now you can do algebra and get fancy with it. Just basically go ahead, grab your calculator and calculate what is 4.2 squared. Okay, so I'm going to grab my calculator right now. I hope you have your calculator with you, and just go 4.2 times 4.2 or 4.2 squared, and the answer here is 17.64. Okay, so we have here a cubed is equal to 17.64. So what is a? Well, take the cube root of it. Now, if you have a scientific calculator, that will just, there is a button that is dedicated to that. So you can simply take that, but I'll show you a different way. So if you have a button that where it allows you to calculate the cube root, I'm looking at my calculator, I'm trying to see it, it's right here. So basically you go, a is equal to the cube root of 17.64, and you can do that. Another way, if you don't have this button, some calculators don't have it, you can do, what is the cube root of a number? Let's say the number is n. The meaning of it is that n to the power of 1/3. Okay? I hope you know that, right? You know, the square root of 9 is 3, and the meaning of it is that the square root of 9 means 9 to the power of 1/2. Basically, whatever nth root here, this nth, let me put it here. So if I have a nth root of x, that's basically x to the power of 1 over n. You see what I'm saying? Whoops. So it's 1 over n. Okay, so the one that you really need to know is the cube root, because Kepler's third law, we're going to be using it several times during the course. So, the cube root of a number, if you don't have the cube root in your calculator, so it will be to the power of 1/3. Now, 1/3 is 0.333. You see what I'm saying? So I can write this number, a to the power of 17.64 to the power of 0.333. Now I can do this with my calculator. So I can go 17.64 to the power of 0.333, and the answer is 2.6. Okay, again, you can do this only if you don't have a cube root in your calculator. Got it? I hope you get that. Here's an example, another example. So basically, there we go. I mean, let me just brush up. I forgot to. So Kepler's third law. So it said, okay, so we have this planet. It orbits its own star. It takes it 4.2 years to orbit its own star. How far is it from the star? Okay. Well, how far is it? It is 2.6. We call that 2.6 AU, astronomical unit. Okay. Again, we'll talk about that later. Astronomical unit is basically the average distance between the Earth and the Sun. We call it astronomical unit. I'm trying to put that A here. There we go. Okay. All right. Another example. Let's say, for example, I have a sphere. That doesn't look good, does it? I have a sphere, a ball. Okay. And let's say the radius of the sphere is big R. We're talking here geometry, okay? And I want to know what is the volume of the sphere. Volume. What that means, the volume of the sphere means if this sphere is a spherical shell, okay? Let's say the sphere inside is empty, okay? If the sphere inside is empty, and I want to fill it up with water. How much water would that be? How many gallons of water I can put in there? Okay, that's called volume. You got that? Okay, so the volume of a sphere is 4/3 pi r cubed. It comes from geometry. Okay, that's geometrically speaking, the volume of a sphere is 4 pi r cubed. Okay, you got to run across this formula a couple of times during the semester because we talk about the Earth or some planet or some stars, and given the radius of that star, you may want to calculate the volume, or the density of it. We'll come back to the density in a minute, but as you know, the density, D, is mass over volume. So if I want to calculate, let's say, the density of the Earth, and I know the mass of the of the Earth, but what is the volume? Well, the Earth is a sphere. If I know the radius of the Earth, like here, so I can calculate the volume, you see what I'm saying, to get the density. So anyway, so let's say, for example, I am given this formula for the volume, and let's suppose that, let's take the Earth, for example. So let's apply it to the Earth. So I have the Earth, radius of the Earth is 6.37 times 10 to the 6 meters. I've always memorized this number. That's the radius of the Earth, okay? If the Earth, which basically almost 6 million meters, the radius, okay? So what is the volume of the Earth? How big is the Earth? So basically what we do, we plug it into this formula. So we have V equals to 4/3, 4 over 3, times pi, which is 3.14. I hope you know that, right? And then r cubed, we take this number written in scientific notation, 6.37 times 10 to the 6 meters, quantity cubed, okay? Now, again, it is best if you have a calculator, scientific calculator, to do that. So all you need to do is maybe you want to start with, let me change the color. Maybe you start with the volume here, and you plug it into the calculator, 6.37 times 10 to the 6, and then you cube that number. So that's what I'm going to do right now. 6.37 to the power of 6, and then I'm going to cube it, which means I can multiply it by itself 3 times, or I can just do the power of 3. And the answer here, I still haven't worked with this yet. The answer would be, if I look at the calculator, it's a big, big number. So if let me write down exactly the number that is shown on the calculator. 2.58474,853 times 10 to the 20. Okay, that's the number that I'm seeing on the calculator. It looks like a credit card number. Okay, so you don't need to write all that. Okay, so all you need is really maybe 2 digits after the decimal point to the right of the decimal should be good enough. Okay, so if I want to write it down, so basically this will be 2.58. That should be good enough. Okay, so you don't need all that. Times 10 to the 20. There we go. So that's basically this value, this quantity. The radius cubed. I get this. Now the next step is to multiply this number by 4/3 times pi. That's not difficult, right? So basically I can do it with my calculator again, 4 pi over 3. So let's do that. So 4 times pi, which is 3.14, divided by 3. The number here is, again, if I want to write the whole number, 4.18666, a lot of 6s, 7, times 2.58 times 10 to the 20. Again, I don't need to write all of that. What would be good enough for this is 4.19. You see what I'm saying? Because if remember, you want to put just only 2 digits, that should be good enough. And since this number 6 is greater than 5 or greater, so this 8 becomes a 9. I'm sure you know that. 2.58 times 10 to the 20, and then I would just multiply the whole thing together. 2.58, 20. Final answer is 1.08 times 10 to the power of 21. Okay? Meter cubed. That would be the volume of the Earth. This is how big the Earth is. This is how, in other words, think of it like if the Earth was empty inside, how many amount of water I can put in there, that'd be this much. Okay? It's a huge astronomical number. Okay, so let's continue. Let's say I want to find the density of the Earth. So as you know, the density, D, or sometimes it's written as the Greek letter rho, okay? So you may see rho or big D for density, okay? So density, or rho, is mass over volume, right? And the mass of the Earth, I can go back and let me go back to the web. Mass Earth, right there. It seems like I've looked it up already. There we go. It's roughly, as you can see, it's written in scientific notation, 5.972 times 10 to the 24 kilogram, right? And that's the number we want. So I can, let me just approximate it, 5.972. Let's just make it approximately 6, okay? So 6 times 10 to the 24. So that will be equal to get the density of the Earth, 6 times 10 to the 24 kilogram, divided by the volume. I have already gotten the volume right there, 1.08 times 10 to the 21 meter cubed. Again, I use my calculator. So I have 6 to the power of, times 10 to the power of 24. 6, I want to do it again. I made a mistake, I think. Divided by 1.08 to the power of 21 times 10 to the power of 1. And I will get the, if I did it correctly, it is 5555.55, you know, forever. Okay, I want to write it in scientific notation. I mean, this is, since it's only a 4-digit number, it probably looks cute. You can keep it the way it is if you want to. Maybe you can go 5556. That'll be kilogram per meter cube. That'd be a cool number, a result. Or you can use scientific notation for it. So how do I do it? Well, the decimal is right here, and I'm going to move it 1, 2, 3. So it's going to be 5.56 times 10 to the 3rd kilogram per meter cube. Whichever way you want it. This one is correct. This one is correct, and so on. Okay? Okay, good. Let me look at my notes, and I will be creating several videos throughout the session, and especially when we deal with a new equation or a law, mathematical law, I will be creating a 5 to 10 minute video on how to use that law, and and so on. So let me, okay, one more thing I want to talk about, and that is geometry. Let me just switch to geometry. What is called conic sections. Geometry. Okay. We have something called conic sections. For those of you who have taken maybe pre-calculus in high school, you probably run across it. Definitely if you've taken calculus, you've probably seen it. But if you haven't, that's okay. I'm not trying to scare you or anything. But basically, the reason it's called conic section, because there are 4 shapes that actually come out from the cone, from cutting a cone. So as you know, the cone looks something like this. I can draw a cone much better on a pencil and paper rather than a pixel. I'm not very good with it. But anyway, there we go. Here's a cone. If you cut the cone like this, let's say I have a scissors, all right? And I have this cone with me, and I would cut it horizontally like this. Horizontal cut, okay? And then I would look at, here's my eye. I look at it on a top view. What would I see? I will see a circle. Make sense? The rim of the cone would be circular. That's what I'm trying to say. The rim of the cone would look circular. Okay. However, if I would take the original cone now, okay, and I would cut it like this with an angle, okay, and I look at it. Here's my eye again. I'm looking at it. What I'm going to see? I'm going to see something like this, kind of an oval shape. You see what I'm saying? Now, also, if I would cut it, go back to the original cone, and I would cut it vertically like this. Okay, what I will see, let me just eliminate this. What I will see, and if I would have my eye here looking at it, looking at the cut, what I will see this. That's called a parabola. A parabola. Okay, sorry, I forgot to mention, this is called an ellipse here. Ellipse. That's called a parabola. Now, again, if I would take go back to the original cone and I would cut it, see this vertical cut right here? I want to make it a little bit slanted, like this. Okay? And I have my eye here looking at the rim or the cut itself. It will look like a parabola, except that it opens up quickly, like this, maybe. More divergent, if you will. Wider. It's kind of hard to draw. Anyway, it's called hyperbola. 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 Yeah. I'm writing at the edge of the screen. You're probably not knowing that. It's called hyperbola. Hyperbola. Okay? So it turned out that, believe it or not, all objects in the heavens, as they circle around other objects, the path or the trajectory that they follow, it's one of those shapes. Can you believe it? In other words, the moon around the Earth it takes almost circular shape or elliptical shape. When you have a rock going toward, let's say here is for example Jupiter, okay, and you have a rock coming from very far away, and it goes like this, and it just flies away again, coming from very far away, and it goes out to far away. That shape would be a hyperbola or a parabola. Okay, and so on. So, or you have some object coming in, and then it would become gravitationally bound to Jupiter. So it may go like that. So it would take that elliptical shape, or it could be a circular shape, and so on. Okay, so all the shape of the path of all objects in the heaven, they take those, what we call the conic sections. It's amazing what that is. It's really amazing. So, but most of them really take the shape of the ellipse. The ellipse is more common. Okay? So let me talk a little bit about the ellipse. For those of you who've taken pre-calculus, you're going to find this pretty trivial, because I know you studied them in a lot of details. But you don't need a lot of details. All you need is just the basic thing. What is an ellipse? Okay? So the ellipse, it looks something like this. This is how you probably would your math teacher in junior high would teach you. The ellipse, like I said, it's oval shaped like that. Okay, I'm unable to draw it in a nice way. There we go. I'm trying my best. Okay, imagine that I have X and Y on it, just for. Here we go, the XY coordinate. It's not good. One more. There we go. Okay. This is the center of the ellipse. Okay, this is the ellipse. Let me just write it down. So this is the center of the ellipse. Okay, and there are also 2 points on the ellipse. They are called, each of them is called the focus. So this is the center. Let me just trying to get the color. There we go. So this is the center of the ellipse, which is right at the origin of the coordinate system X and Y. You see what I'm saying? And this is called the focus. We have another focus here. They're both identical and symmetric. Okay. The plural of the two is foci or foci. Depends on which Latin you use, classic Latin or church Latin, I heard. Anyway, so each of them is called a focus. Now, those two foci, if I make them closer together, if I move them closer until they both meet right at the center, what will happen? That the ellipse becomes a circle. What I'm trying to say is, a circle which, as you know, it's probably, as you know, it only has one point, the center of the circle. It is actually a special case of the ellipse where the two foci, those two foci, meet at the center. Okay. More on this. The distance from the center to the edge of the ellipse here on the x-axis, we call it the semi-major axis. And the distance from the center to the edge of the y-axis here is called the semi-minor. Okay. Notice that if I take, let me go back to the two foci here. If I bring the two foci together and to meet right at the center, it will become a circle, correct? Which means this semi-major axis is exactly equal to the semi-minor axis. Notice that? Remember here, the semi-major, because it's longer, so they become what we call the radius. Okay? So the circle is kind of think of it like a daughter of the ellipse, or a special case of the ellipse, where the two foci meet at the center, and the semi-major axis of the ellipse and the semi-minor are equal. You see what I'm saying? That's what the circle is. Okay, now what will happen if I would take the two foci and I bring them farther away from each other? What will happen to the body of the ellipse? What will happen is that it will become elongated. It will look something like this. Let me go back to a black color. It will look something like this. If they are really far away from each other, it will become really elongated like that. So where this is the center, and now the two foci are here. You see what I'm saying? So it becomes more elongated. So we have a concept, or a parameter. We call it the eccentricity. This is important. The eccentricity E, or the Greek letter epsilon. Eccentricity basically tells you how deviated the ellipse, or how far is it from being a perfect circle. Okay, how far the ellipse from being a perfect circle. Now, for the eccentricity of a circle is 0. And the eccentricity, basically, it's somewhere between 0 and 1. 1 basically means the ellipse is extremely flat, like this. I mean, extremely flat. It's the extreme case where the two foci are actually very, very far away, almost infinite. Okay? And we call that the eccentricity equals to 1. Okay? And the 0, as I said, is a circle. So when we say, for example, that the moon's eccentricity around the Earth is 0.065, as you can see, this number is very close to 0 and much farther than 1. What that means is that the moon's orbit around the Earth is almost circular. Okay? In other words, the closer the number to the 0, the more circular the path is. The closer it is to 1, the more flattened it is, or more eccentric. You got that? Okay. One more topic, and I think this is the last topic I want to talk about, and that's called the angular size. Again, this is still geometry. So what is angular size? Let's say, for example, you may remember, if you have a circle, Here's the center. And let's say, for example, here's the radius. Here's the radius. If you remember, we call this the arc. S is the arc. And this is the radius R. And this is the angle theta, right? There is a relationship. It's an extremely important relationship between the arc, the radius, and the angle. So we say that S is equal to R theta, okay? Very, very important relationship. Where theta here is the angle, and it is measured in radians, not in degrees. For example, let's say, for example, let's assume that this circle that I'm dealing with, let's say it's a track, very, very large track. So let's say I start from, let's say right here, here's someone standing right on the track. And let's say this person start walking until here, okay? There's the person when he arrived here, let's say, okay? So this is the how far did the person go, S. And the radius of the track is R, and this is the angle, theta. So the question is, if I give you the radius of the track, the circular track, and I give you the angle theta, this angle right here, how far did the person go? Well, basically S equals R theta, provided that theta have to be, like I said, in radian. What does that mean? Okay, let me tell you what that means. Let's say that the radius, let's say 10 meters, for example, okay? And let's say the angle 60 degrees, okay? What you want to do, you have to convert it into radians. What that means is that you take the 60 degrees, you divide it by 180, okay, degrees, times pi. That's basically how you convert. Then I'm going to use my calculator. Remember, pi is 3.14. So I have 60, oops. My pen is not working very well. I think, okay, there we go. 60 divided by 180 times 3.14. So basically 60 divided by 180, I'm using my calculator, times 3.14. Answer 1.045. 1.0, I mean, let me tell you what's displayed in my calculator. 1.04 and then 6666 forever, okay? So basically you can, rather than writing all of that stuff down, you just go 1.05. That should be good enough, okay? So there we go. So this is the angle in radian. So 1.05 is exactly the same as 60 degrees, but that's the one we use. You never ever use degrees. So now back to our formula. S equals R theta. So R is 10 meters, we said, and theta is 1.05, and that will give me 10.5 meters. Okay, so the person have walked from here to here 10.5 meters. You got it? Okay, the converse is also true. So let's say, for example, let's say I have that circular path that we're talking about, okay? And let's say I know that the arc length here, let's make it 5. Okay? 5 meters, the arc length. This is S. I'm just, guessing numbers. And let's say that the radius here, let's make it, let's say 7 meters. Okay? So what is the angle? Okay? This angle, we call it, like I said, I forgot to tell you that it's called the angular size. So, okay, in a minute. Let's find theta in this case. So we know that S is equal to R theta. So I need to solve for theta is S over R. And that will give me basically 5 meters divided by 7 meters. And I'm going to use my calculator. So 5 divided by 7. And that will give me 0.71. 0.71. Again, the number in my calculator, let me write it the whole thing down, which you don't need to, but I want to show you how to round it. 0.7142857143. All these numbers are really meaningless because we're dealing only with one digit here and one digit, so we would expect to get all these. So anyway, so you don't need to put all of them. So basically 0.71 radian, automatically that will be in radian. Okay, now that should be good enough. You're not going to be asked to convert it to degrees, but if I want to, you don't need to. That's optional. So how do I do it? Well, it is 0.71 radian. So what you do, you divide it by pi, and then you multiply by 180. Kind of do the reverse of what we've done at the top. Remember that? What is it? Right there. So we have the angle in degrees. We divide it by 180 times pi. To do the converse, you divide it by pi and you multiply by 180. You know what I mean? So there we go. We can do that. So I can multiply this by 180 divided by pi, 3.14. Final answer is 40.95. Yeah, that's fine. There we go. And there we go. That's theta. So the reason I'm telling you this is because there is an equivalent way of speaking about somebody, let's say, going around moving in a circular path. I can say this person moving in a circular path with an arc length of what we found, whatever it is, what is it, 10.5, or we can say that person is moving in an arc in a circular path with 1.05 radians, right here. Okay, this will become important when we start measuring distances and what it's called, a concept called parallax. It's a very interesting concept. We're gonna study it during the course. And that parallax is really based on this basic geometry that you have studied in mathematics. Okay, so I'm going to stop here. There are more topics that I could cover, but I want to reduce it. I don't want to take up more than 1 hour for this. This is just a beginning of hopefully a series of other videos that I'm going to be creating. But the rest of the videos, hopefully, they're going to be somewhere between 5 to 10 to 15 minutes only. Just little bits and pieces to help you, go through the course and hopefully enjoy astronomy. It's one of the most fun classes that you will take in your college career, and I look forward to working with you. Have a wonderful semester. Bye-bye.